The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
My name is James Gerasi. I worked with Sudarshan and John Chu on this project, and what we did is we took a numerical simulation, electrochemical simulation of a battery, and ported it to the PlayStation 3. So the objective of this project for this situation was to port a electrochemical battery simulation to the PlayStation 3 and try to take advantage of the unique features of the cell processor to help speed up the computation of the simulation. So when we talk today, we're going to talk about why we would want to do that. We're going to discuss the model, we're going to discuss how we solved it numerically, look at some of our performance results, and then discuss what we wish we could have implemented. Okay? So the justification is basically the world needs energy. And oil has been in the news a lot and hasn't been as a reliable source of energy as we'd like. So in the automotive industry, hybrids seem to be part of the solution to the energy needs. Now, one of the problems with hybrids is how much energy is in your battery. So the more sophisticated battery model that we can put in a hybrid, the better that we're going to be off. So a more sophisticated model requires more computation. So you're looking at having a large superscalar processor in your car, or you could see if you could get a lot of small processors to do the same amount of work. And the cell represents the kind of the first opportunity to be able to test that out. So the simulation that we ran basically consisted of a lead-acid battery cell. So unfortunately, they use the word cell, and we're also using the word cell. So it's sort of like the modern-day Smurf. But so in a lead-acid battery cell, you have a lead dioxide electrode, which consists of a number of parts, a lead electrode, which also consists of a number of parts, and an electrolyte, which is 5 molar sulfuric acid, which consists of H2SO4. Okay? When you discharge the battery, you're going to close the circuit, and basically what ends up happening is you have electrons flowing on the outer loop, and between the electrodes you're going to have an ionic current. So you have a complete circuit around your loop, and this is the effect that the simulation is trying to simulate. The simulation works on a very low physical level, and it simulates the chemical reactions, which at the lead dioxide electrode, it converts lead dioxide into lead sulfate during discharge, reverses it during charge. During discharge, the lead electrode turns lead into lead sulfate, and during recharge, it converts that back. To implement the model, we took basically and discretized the system and just kind of cross-sectioned it. Okay, took small sections and cross-sectioned it. We're going to skip this slide. But basically, to simulate the physics, we have a bunch of nasty nonlinear coupled partial differential equations. This is an example of 2 of them, and there are a number of other ones that are included in the system, but not really worth seeing. Just kind of a feel you get. You see a diffusion term. You see in the lower equation, you see a diffusion term. You see a reaction term, and the upper equation, you see changing of the porosity, changing the geometry of the system. This is kind of the output that you could get from this type of battery simulation. And what you're looking at here is you're looking at if the left-hand side is the electrodes, is the top of the battery, and the height of the battery goes along that way. You see that as you discharge, the concentration at the top of the electrodes is the acid is consumed where you're drawing current out most readily. So physically, the simulation kind of makes sense, even if my speech didn't. The battery model that we use is a 2-dimensional model. It has both a lead dioxide electrode and a lead electrode and an electrolyte area. This is an example of just the lead dioxide electrode. And if we discretize that in 2 dimensions, we would get a discretization that looks like that if we were to use a single-centered finite volume method. But it turns out that we have so many discontinuities in here that it's much better to use a staggered grid. And so we are using a we're using actually two different meshes to simulate the system. Two different meshes. Well, on a single mesh, you would end up having 4 corners, 4 edges, and centers, so you'd get 9 different types of objects in one electrode alone. And you're talking about a rather large and nasty simulation. On a small scale, the simulation would produce a very sparse matrix that looks something like this. And Sudarshan will now come up and talk to you about the matrices and how we solve this system.
So basically, like John said, the problem we're essentially trying to parallelize the most computationally expensive part of this whole simulation is solving for the Newton the Newton iterations during each load step. And so basically, in an abstract, I'm sorry. Any questions? Sorry? The microphone. I'll try, but you've got to try and listen harder too. I got it. Yeah. Is it any better now?
No, you gotta yell at them.
Is it any better now? Yeah. Okay, cool. So yeah, I always like to say, I'll try to speak harder, but you should try to listen harder too. So we can meet somewhere in between. So basically, in the abstract sense, we are trying to solve a system of sparse linear equations, and for simplicity, for the first pass, we treated the matrix as being dense. So we did the whole Gauss elimination on ignoring all the zeros of the matrix. And so the basic idea is that we do the full, we do Gauss elimination with partial pivoting, and it's the forward elimination stage of the Gauss elimination that's order n cubed that is most expensive, and that is the thing that we've tried to parallelize among the SPUs. The partial pivoting and the partial pivoting and the backsolve is all done on the PPUs because that turned out to be much faster. So this is the matrix that we are considering during each step, filled with random entries and filled with the random right hand side. The way Gauss elimination works is that we start off with one of the rows which you call the base row, or which is where the pivots come from. And then we take all, and then we eliminate the variable corresponding to base row from all the subsequent elimination rows. And all these eliminations can be done in parallel, and that's what we have tried to parallelize. So each SPU grabs hold of the next available elimination row, eliminates it, and writes the result back onto the main memory. So, for example, if we consider a situation with two SPUs, what we do is that we stream the rows across we stream the elimination rows across all the SPUs. Each SPU performs the elimination and writes the result back to main memory, as you can see. And this happens for every row. So in this simulation, the first variable has been eliminated. As you can see, there are zeros along the first column, and then the process is recursive. After the first variable is completed, it moves on to the next variable. So that's basically how. And as you can, and the way the elimination rows are dealt out, they are dealt out in a cyclic fashion. So there is no serial bottleneck. It's all perfectly load balanced. I'm sorry. I'm sorry.
When you eliminate something lower, doesn't the pivot value change? I'm completely not getting what you are saying. That's my first question.
Yes.
Second question is, it is sparse or dense? What's your matrix representation?
The matrix representation currently is dense.
Okay.
Yeah, so...
And doesn't the pivot value keep changing when you eliminate? So is it completely parallel? And that's what I don't understand. What's the parallelism? What are the dependents?
So the elimination, all the subsequent variables that are eliminated for each variable can be done in parallel. But after one variable has been eliminated, there's a synchronization step where all the SPUs have to synchronize. There's a barrier after each row has been eliminated. Yeah, so you start at so there's a triply nested for loop if you write the algorithm down, and the first and then it's the inner two loops that are completely parallelizable, and that's the second loop is what we try to parallelize. Is that a little clearer? Yeah. So this is the basic algorithm, I'll let John talk about some of the performance numbers we have got, but some of the optimizations that we have tried to, that we haven't done are the use of last 3 operations where you stream multiple rows at a time, and the use of SIMD operations. But I'll let John talk about the performance numbers.
Computation of the current elimination row with the fetching of the next elimination row, we get roughly a 30% speed up. So here's a graph of to see how both the unbuffered and buffered version perform with a number of scaling with a number of SPUs. So as you can see, both look roughly pretty linear, and that makes sense because and so here's another graph of how we scale with the size of the matrix that we're working with. So the smaller the matrix, the higher the computation ratio. So the communication latency should be more apparent. But as you can see, even as you get smaller, the computation is still pretty linear. So.
Yeah, it's linear, but it's not it's not a sublinear. It's not running at 2x performance improvement. But it has a very nice, it's not flattening out. So the interesting thing there is, why is it only 30%? Why is it not 2x, giving 2x performance improvement? So is it because of underslope? If it is underslope, this graph shouldn't have this kind of a pattern. It should kind of have a more exponential type pattern. So I'm not understand.
Do you understand the question?
No.
Why aren't you getting 2x speed up? Or, I mean, your line is straight,
Yeah.
but it's not increasing proportional to the number of SPUs you're increasing. So your efficiency might not be at 100%. Any idea why?
Wait. The 2x would only, this is a log clock, so 2 would only shift it up and down, right?
Yeah, so it looks like you're not operating at 100% efficiency, right?
Oh, it doesn't matter.
Yeah.
So I think some
Kind of in the conversation going on there. But this is a strange type of a graph because if it thinks linear, it goes actually 2x kind of improvement and you get a very nice linear thing. If you have underside overhead, what you get is you have a good speed up at the beginning and then you slow down. You get a kind of a logarithmic type of a graph. So it's very hard. I haven't seen things like a straight line, but not as 45-degree angle graph. So this is kind of a strange thing. It might be interesting to see where and why this is happening.
Okay. Well, yeah. So I'll just move on. So I'll talk about some of the further work we're trying to do.
John,
Yeah.
can you just clip to your... Yeah.
So we've also tried to triple buffer by pipelining the fetching of the next row with the computation of the current row with the sending of the previous row. We did this, but it didn't actually give us the speed up that we thought we would get. What we're working on now is syndizing the computation stage. So right now we treat the rows as, all the doubles in the rows as scalars, but we could use by syndizing, hopefully we can get a speed up of by a factor of 2. And also right now, our LU algorithm isn't very smart in that when we fetch the elimination row, as we go on through the algorithm, part of the elimination row becomes zeros as we move down. So we don't really need to fetch the entire elimination row. And so by taking that into account, our memory, our DMA transfers are smaller, and maybe that'll speed things up a bit.
So the whole thing is in double precision?
Yes.
Do you know how many megaflops you're getting?
We have gigaflops. I think we're getting around 2 gigaflops.
So here's a gigaflops.
Yeah.
Do you know what the expected for the algorithm, like the theoretical?
David is made up algorithm by us. Just wanted to help us on this field.
Is this a linear scale or on the y-axis now?
Yeah, that's a lot.
Any idea why you have this artifact 3 SPUs?
Wait,
Your double buffering result just drops.
Actually, we have no idea.
No idea.
It was not, I don't know if we consistently checked it.
You might want to run it a few more times.
Yeah.
There is a recent series of papers by Jack Dongar's group where, aiming at double precision calculations, they used single precision to get an approximate guess,
Right.
and then did a few iterations of an iterative approach to get a double precision result.
Yeah, those don't work very well for fully conditioning matrices, though. That base thing. And this is conditioned on 10 to the 8. So that's kind of out of the part of the true precision.
And the particular work that you're referring to, they try to do only JavaScript decomposition. The main reason they do JavaScript is because they say the performance goes down dramatically after checking. That's one of the things that we try to practice our symmetric system. And we're doing things, the hope is to generalize this to sparse matrices later on. And not, I don't think, I think they are trying to do some work with sparse matrices, but they haven't gotten there.
One additional question, just at a high level, is this the right way to tackle this particular problem? It strikes me that there must be a closed form, high-level macroscopic model for the battery self-discharge. I don't know anything about the chemistry of lead-acid batteries, but the little write-up on the website mentions black shoals, which I do know something about, and of course there are efficient ways of doing that without.
Sure, there are efficient ways of doing black holes. There are different ways of doing this. This is only one of the equations is similar to black holes.
Mm-hmm.
There are multiple equations that go into this. They're all coupled. They're all nonlinear. So solving this system of equations is in the literature. If you were going to choose this as your model.
But if you were actually in the business of
well,
building and
well, see, the problem-
batteries, wouldn't you try and come up with an efficient macroscopic model rather than
it depends on what your compute costs are. I mean, if you are going to run a model on a superscalar processor, that's a very expensive processor. If, however, now you have the ability to use a collection of small, cheap, little processors like this, you can maybe have the luxury of using a much more sophisticated model. So,
is it necessarily more sophisticated? I mean, is there some fundamental reason why you get more information out of this approach than out of a higher level model?
you get a lot more detail as to what's going on within your battery. A high level model will give you I/O information,
Mm-hmm.
but if you're trying to find failure mechanisms, you may want to know how much pressure is going on at certain points in your battery. Especially with like lithium-ion batteries, when you this differs from a lithium-ion battery in that we're actually changing the state, the type of matter that we're using. And in a lithium-ion battery, we're intercalating and deintercalating. And so what we're doing is we're creating a lot of stress on a matrix,
Mm-hmm.
a crystal, and that will be a failure mechanism. A simple input-output relationship will not give you that failure mechanism. So you may want to know that kind of information. You may want to know heat information also. You could include thermodynamical information into this kind of model.
Okay, that's a good answer. I take that to mean that the reason for doing this is if you're researching the physics of battery discharge as opposed to trying to estimate how much power is left in your battery.
Well, you could use it if you have the computation power. You could use the same model that does the research as is the car. And so if you can use a small processor with it. So our demonstration, if you guys want to see printf statements.
I think we're
Otherwise-
over time.
Yeah.
Any last questions?
Wait, just still trying to understand the sparse versus dense issue. And you
Okay.
can just do a sparse elimination on a uniprocessor. Do you get a bigger speed up?
Oh, you get a much bigger speed up.
Okay.
The sparse is, the LU is about the
Yeah.
slowest thing you could possibly
Sure.
choose, but it works. And
Okay,
since
but
we
what you have would still be useful for dense matrices?
It'd still be useful for dense matrices.
And did you
yeah.
compare it all to just PPU performance on a dense matrix?
No, we didn't compare it to the PPU. We had to compare. We have the same model running on a PC. So.
Okay, thanks to speakers.